Thank you. So this is work in progress. It was originally planned to be a complete work, but unfortunately we didn't make enough progress, so it's work in progress. This is joint with my student Jack Dark. And one of the ways that it's work in progress is this work has no application. What I mean by that is I've got no slide that says here are all the applications. This is algorithmic work where we hope that the problems we're thinking about are suitably general, that they will fit a number of possible applications, but again we sort of started with the algorithms and we'll see what consequences that leads us to. So the starting point of this are these data structures that have been developed in the computer science community called sketches. And these sketching ideas connect deeply with lots of other topics that people are interested in. They connect to compressed sensing, they connect to, they're also known as random projections. So I should say what I mean by a sketch. I'm thinking of ways of taking a large amount of data, probably for the most part data I'm going to think of as represented by a high dimensional vector, and I'm going to come up with some more compact representation of it that I will think of primarily as a linear transformation. So in other words, I'm going to take my data X and I'm going to apply some sketching transformation to that data, and I'll get some summary that I'll call the sketch of data X. I'm going to be interested in transformations that I can write where S is some matrix, some structured but random matrix. Why do I want to think about this restricted class of objects? Well, a couple of reasons. One, they come with nice properties. So as soon as I talk about linear transformations, then I get the property that I can take two pieces of data, X and Y, combine them, scale them up, scale them down. And the sketch of a linear combination of X and Y is the corresponding linear combination of the sketches. So this, again, talking rather abstractly, is my sort of roundabout way of saying this is something that's going to suit data that's very large, so I'm actually processing it in different places and combining the sketch summaries. It's going to suit data where I've built a summary of everything I've seen so far, and then either some new unit of data or some new block of data arrives and I want to update my summary of it. And it's also interesting because sketches exist. That we know lots of constructions of particular matrices S that capture various properties of vectors that are suitably foundational, that they're useful to us. So sometimes we'll think about sketches in terms of this sort of linear transformation terminology. Sometimes, more computationally, we'll think of them in terms of hash functions, because if I do think that X is so vast and high dimensional that I would never want to store it explicitly, then for sure S also has that characteristic. So I never want to think of really materializing S explicitly. I want to think of drawing columns of S or rows of X when I need it. So those columns or rows are going to be described in terms of hash functions that are compact and easy to kind of essentially materialize individual entries of the sketch matrix on demand. And from now on, I'm really going to treat these sketches as a black box, because we don't need to know too much about them. The property of sketches I'm going to use today is I'm going to use the fact that there are particular sketch constructions that allow me to estimate vector inner products. Right? So if I build a sketch of vector X and a sketch of vector Y, I can combine those two sketches and get an estimate of what's the inner product of X and Y. And these are compact, so they're kind of essentially independent of the dimension of the input vectors. What do I mean by that? I mean, if I choose my sketch size to look something proportional to 1 over epsilon squared for a parameter epsilon, then I'm going to estimate this in a product with additive error. So whatever the answer is, plus or minus some error that looks like epsilon times the product of the two norms. Okay. So that's the black box, that's the assumption about sketches that I'll be using. And what I'm going to talk about today is an attempt to sort of take that black box and build on top of that a more complex data structure, a more complex algorithm that lets us study correlations. What do I mean by correlations? I mean exactly what you think of when I talk about correlations. I mean, you have some series of data, two series of data, let's say something that will give you some x values, something that will give you some corresponding y values. And you want to say, is there a linear relationship between these? So you can have no end of fun looking up this web page of spurious correlations that's essentially taken large quantities of data and gone through many pairs and seen when is there a very high correlation between things for which it would be hard to posit any causal relationship. So this is one I picked out. It's showing total revenue generated by entertainment arcades versus computer science doctorates awarded in the US. And you'll see the two series seem to travel together pleasingly closely. Okay, so the problem I'm trying to think about here is to say, let's say I've got a very large collection of time series, and so very many time series, and each time series is very high dimensional. And I want to pull out which are the highly correlated pairs. Okay, and rather than looking for spurious correlations, I would rather find meaningful correlations. Right, so I'm going to hope that what I find is meaningful. Okay, so let's introduce some symbols. M is the number of observations, M is suitably large, and N is the number of time series, N is also suitably large. And we might think about doing this, if my concession to real time is to say that, well, maybe we're seeing new observations of these. So this is not a static fixed data set, this is a growing data set, So, if you want to start dreaming about applications, you can think of, telecommunications networks or global scale data centers or whatever else seems like it might generate lots of data. So what do I need to do here? When I'm looking for correlations, I'm thinking of the time series as sort of essentially being draws of random variables. The covariance is a first attempt to capture the interrelation of the two series. And that's basically, I'd like to look at a quantity based on the expectation of the product minus the product of the expectations. And the correlation is just an appropriately normalized version of the covariance, right? So all I'm interested in is, for any given pair, being able to pull out the correlation of that pair. And given, actual data, I can just, plug in and compute. So if time was not an issue, space was not an issue, I just wanted to do this computation, what would I do? Well, one plausible thing would be I would, for each input series, I would create some appropriately normalized version of it. So essentially subtract off the mean of the series and then divide through by the standard deviation. And so that lets me then reduce to inner product, because the correlation between any pair is just the inner product between the corresponding vector representations. So what's wrong with doing the exact thing? You need this pre-processing, this normalization, takes time proportional to the number of series times the number of observations. Well, nothing wrong with that. That is the size of the input. So if I'm prepared to look at all the input, then I'm going to incur that kind of cost. But what hurts is this kind of search, right? And this is not unique to this problem. Lots of other problems run into this quadratic bottleneck where you're essentially trying to compare all pairs. And if you do explicitly compare all pairs, you hit an n squared term times m to actually run through those entries. Right. So I might be able to squeeze this a little bit if I start thinking this is a matrix computation and I have an appropriate fast matrix multiplication algorithm that might gently reduce some of these terms, but I'm not significantly going to win here. And again, if I believe that n is sufficiently large to make this painful, then n squared is definitely going to grow faster than I'd like it to. So why might we hope to do anything better? So certainly if there's a reasonable chance that any given pair is correlated, some constant chance that any given pair is correlated, then I'm pretty much going to, and I want to report all of those correlated pairs, then I'm just going to have to incur something essentially quadratic. So I'm going to be thinking about situations where most things are uncorrelated, most things are sort of randomly, unrelated.
Is that clear that, even if many things are correlated, you can hope to report clusters of correlated things in linear?
Yeah, so I'd need to introduce some extra structure. So yeah, maybe I'd actually have some sort of hierarchy over the series and try and sort of relate them. But in this sort of base version, I don't know a meaningful way to describe such clusters. But yeah, lots of variations are possible here. Okay. So I have a hammer. My hammer is called sketching. I will apply it to this problem and see how far it gets me. So the first thing you'd think of doing is say, well, I've already said that the basic thing that I'm interested in, a vector and a product. Sketches give me that with some noise. So I can take every series, x1 through xn, apply the sketching transformation to each one, and reduce the dimensionality, hopefully. So I've still got n objects, but they're now of dimension b. Does that make a difference? Not hugely. Right, so I've knocked down the coefficient on the quadratic term. Hopefully I've knocked it down. If I've not done this carefully, I might have inadvertently pushed it up. But hopefully I've knocked it down. But I haven't beaten this quadratic term. Right? Because all I've done is I've reduced the cost of comparing any pair, but I haven't reduced the number of pairs, or number of pairwise comparisons that I would do.
So are we to think of this n is bigger than n?
Yeah.
We're to think of m as being large, certainly. It could be m could be comparable to n. If m is very small, then this step won't help. So you might as well just work with the series exactly.
I was just thinking maybe b could be taken to be like square root of n.
Well, it's essentially what this step says is you can kind of ignore m, right? And this again, it comes up a lot with sketching, that although your data originally may have been high dimensional, essentially, to make this work, b has to be at least logarithmic in n for the probability to work out. But because you can do this, you can kind of ignore what m was to begin with and just assume that you're now working with short enough sequences. Okay, so essentially we have a sort of an algorithmic search problem. We want to say where are the significant correlations. So let's sort of flip around that comment from earlier that said if most things are correlated, you can't beat that. If most things are uncorrelated, then there's no point trying everything. You'd like to essentially find clusters of uncorrelated things and say, right, I need to do no further work on these clusters. So the kind of the high level idea you'd like to put into practice is to say, let me do some kind of clustering. Well, the clustering doesn't have to be at all sophisticated. It could just be essentially simply random grouping. Right? And the hope that we'll try and formalize is to say, if I sort of group a bunch of signals together and do nothing more sophisticated than add them up, and I take another group, similarly sum together, and I look at sort of the inner product between those sums, then if there's no correlation of any member of those two groups, then hopefully the sum should be uncorrelated. And if there is a correlation, it should be preserved. So the work to do is to take those claims and turn the should be's into something slightly more precise, which can be formalized without too much pain. And secondly, say, okay, well, if I do this, then for sure, when I find no correlation, and I'm reasonably convinced there really is no correlation between a pair of groups, I can ignore everything within those groups. But when there is a pair of groups that look like there's a correlation lurking somewhere within, how do I find it? So the solution outline is to say we're actually going to do a couple of things. I've kept talking about groups, so group testing, coding, these kind of techniques are going to appear. And sort of an outer layer of sketching is also going to appear. This outer layer of sketching is to do with the fact that you can certainly imagine situations where things combine in an unhelpful way and a correlation that was present between two groups cancels out in some way. So we need to take some steps to try and reduce that chance. And also we'll just do enough sort of suitable random repetitions that argue that it's unlikely enough to happen once, that we'll repeat it a few times and then hopefully catch it in one of those repetitions. So essentially the next few slides are just sort of taking that outline and fleshing it out a bit more and trying to sort of convince that there is some reason to hope that this approach would work. So if this is my original situation, I've got this n equals 6 sequences going in. I'm looking at this sort of 6 by 6 correlation matrix. The leading diagonal is trivially correlated, but that's mostly uninteresting. What I'm interested in are sort of off-diagonal correlations. So this is trying to represent the fact that x2 is coordinated with x5 and it's symmetric. So what we can do is do this sort of random bucketing, grouping, summation, and almost just putting in pictures what I said in words. We expect that because 2 and 5 are correlated, that 1 and 2 are correlated with 5 and 6. So essentially the fact there's sort of zero correlation between 1 and 5, 2 and 6, 1 and 6 doesn't hide this, and we don't find any sort of additional spurious correlations. And the fact that we've got trivial correlations on the leading diagonal, this is something we can predict exactly and just sort of subtract off the contribution, relying on sort of essentially sort of the fact that everything we're doing is linear.
Graham?
Mm-hmm.
Are you going to say something about the relationship to the Great Valiant?
Yeah, I'm not going to say it, but since you've prompted me, I will. Yeah, I mean, this is sort of connected to Valiant's work exactly on related problems. It's this kind of sort of trying to identify things. We're trying to see what we can do in this realm and how we can sort of play around with slightly different constructions. So if I do determine that sort of within a group it looks like there's a correlation of interest, how do I decode this? There's a few different approaches that we're thinking about. So the basic one is to say we're going to try and decode that by doing sort of within a bucket, I'll do some additional tests, leaving some things out, including some things in, and hope and do that in a structured enough way based on a code, so that I can sort of look at the sequence of results interpreted essentially as binary. Is this combination still correlated? Is that correlation still correlated? Read those off and try and identify where the correlation, what that tells me. So the simplest way of seeing that is when the coding approach is a Hamming code. Okay, so this is sort of a much overly simplified example. So here I'm sort of my cartoon example is if I'm thinking about combinations of sort of individual elements, but the concept is the same. So here I've got the contribution of element 1 that's small, the contribution of element 2 that's large, so I'd like to find it, and a bunch of contributions of other elements that are also small. So the way I might try and use a code is basically, I look at the code corresponding to the binary representation of each index. That's basically what the Hamming code is saying. So element sort of 001 means that in the first row I'll include the contribution of element 1, but not in the second and third row. x2 has a 1 in bit position 2, so I'll include it in the second row but not in the first and the last row, and so on. And in this carefully constructed example that makes sure everything works, it works. So the sort of the thresholded version of row 1 is smaller than my threshold value, so I read that off as a 0. The middle row is larger than my threshold value, so I read it off as a 1. The last row is smaller, so I read it off as 0. Then I can reinterpret that as an index again. That's index 2. That was the heavy element. So it all worked. Of course it worked. It was the example that I chose. It's not going to work in general because of noise from sketching, but also just noise from collisions of elements. Things are kind of going against me if I really do add things up. So I'm going to start from sort of this baseline, but try and improve it a bit. And the first improvement is to say, well, actually, I used sketching to reduce the dimensionality of the series, but I could use sketching ideas again to try and sort of reduce the effect of collisions. Right. So essentially, one of the key techniques in sketching is essentially sort of sparse transformations that involve Bernoulli random variables, or Rademacher variables, if you like. So essentially just using +1s and -1s, surprisingly effective at driving down the variance of the estimators that you get. So rather than just adding up everything in a bucket, if I associate every entry in a bucket with a randomly chosen +1 or -1, that means that sort of decreases the chance that lots of things that I don't want sum up adversarially against me. Sort of the informal version. So the picture here looks like, I'm doing my bucketing into rows based on sort of a random partitioning. I do this sort of multiplication by, you can think of this as a diagonal matrix if you like, but it's just multiplying each row either by a +1 or a -1. And then also doing a masking. This masking by either a 0 or 1 is determined by the code that I've chosen, then sum things up. All right, so that's sort of the outline of the structure, that's the outline of the approach. And it's just then a question, the last piece is just say, well, exactly how am I going to determine those masks? Because here's sort of the real situation. So I've tried to make this cartoon a little bit more realistic. So now I'm looking at the combination of something interesting coming from row I and row J. I and J are correlated. So green is sort of showing when my mask is putting them in the same test. Red or 0 is saying when they're excluded from a test. And it may be, again, just picking some sort of numbers to illustrate a point, that my tests mostly work, but every now and then a test will give the wrong answer. So this should have given an answer that was greater than my test threshold. So in this case, my test threshold is just half. But because of other things that I'm not showing, collisions and other things going on, it may be that I get something that's the wrong side of my test threshold. So if I were to use sort of the Hamming code directly and try and interpret this, I'd get erroneous conclusions. I'd need to kind of reconfigure I'd need more repetitions to get this right. But if I have an error correcting code, then maybe I can still read this as a code word, even though essentially there's a 1 or a small number of bit errors in the code word that I decode. I will still be able to decode this as a correct indicator of combination of I and J. So again, sort of somewhat at a high level, I want to think about what codes can I put in here that will sort of give me the right trade-off between essentially the rate of error correction and the code word length. So you get to almost to a few engineering things here. Right? So because every bit I add to the code corresponding to an extra column here means I've got to do an extra set of sketches for every bucket that I'm materializing. So, those bits really add up quickly. And I can do one or two other tricks to minimize the size of the code that I need. So if I think about the way I allocate elements into the buckets, I can think of that as basically being a permutation over the original indices. and I'll just put everything in a bucket that shares a common prefix in its binary representation, say. Well, in that case, I don't actually need to code up the prefix because everything in the bucket has the same prefix. I just need to code up sort of the tail, the suffix of what goes into the bucket. And then in my situation, I can have just stored the random permutation explicitly and kind of retrieve the indices in the original indexing based on the reconstructed permuted index. And the construction of codes that seems to work well in that we can actually implement it is something based on low density parity check codes. And that's nice, it's clean, it's simple, and it works well with the sketches. That's sort of the outline. There's quite a few details to kind of fill in when you actually do this. You still get errors. So you do the usual kind of tricks that people in sketching and randomized algorithms do. You repeat the whole thing a few times in parallel with fresh randomness. And you sort of say, not did I find something once, because maybe it's a false positive, but did I find it enough times? Right, so I've got if I see something a lot, then I'm reasonably confident it's not a false positive, and I'm also reasonably confident that something that really is there is I do see often enough that it will pass this test. Okay, so there's lots of kind of clunky proof to go through. Nothing particularly challenging. It's just setting up the right kind of random events and showing that they all happen with enough probability and doing sort of the bound over all of these to say that everything works. And I'm not quite at the point where I want to sort of say when I say sub-quadratic, what do I mean? It's going to be n to the 2 minus something not very big, and that's also going to rely on some possibly optimistic assumptions. So again, if you think about how am I going to make this work, I've really got to argue that the things that are not correlated are sufficiently not correlated that I can put quite a few of them in the same bucket as something that is correlated and still be able to see the correlation for the trees. Right? And to really sort of put that in terms of n and make that n term sub-quadratic, you actually need to start talking about those correlations looking polynomially small as a function of n. So there is sort of a question mark here in, it's certainly true in theory, but how well will it work in practice? But it can be fast, I guess, is the other thing, that most of the stuff that you need to do is linear algebraic, and you can kind of bulk things together and throw it into a fast matrix multiply, so you can write it in terms of whatever value of omega you happen to believe at the moment. So I said, it'll work in theory, will it work in practice? This is a question I do care about. So we're at the stage of proof of concept, and the concept being proved is that a smart PhD student can write code that implements the algorithm. That is the concept that I think we've proved so far. So here is just a picture to try and show what's going on. Here is a very small input, 50 by 50, so 50 time series of relatively small dimension 1,000, small number of sketches, small number of buckets and repetitions. I think just enough that technically it's fewer tests than or smaller space at least than if you represented the data explicitly. And what this is showing is these sort of white dots are some planted correlations of varying magnitude. So that is what we would like to recover. That's what the input looks like. This is sort of what you get from one iteration of this. You do find the things you're looking for, which is good. And you get these sort of little grey spots, I don't know how well they show up, which are things that look like they're correlations, but of small magnitude on one iteration. So you do those repetitions in parallel and look for what shows up consistently. What shows up consistently is what you planted there. So proof, if proof were needed, that a graduate student given time and a reasonably powered laptop can produce some nice pictures. So what I've tried to say today is sort of an introduction to this work in progress, and thinking about, we've had sketches around for a while, and they've been very useful for giving us, addressing problems that can be directly represented as vectors. Finding heavy items in vectors, finding how many non-zero entries there are in a vector and so on, which in turn actually have kept people in Silicon Valley quite entertained. There's a small industry in Silicon Valley of people at Google and Facebook implementing these kind of algorithms for analyzing their log data and seeing what their customers are doing. So the interest to me is to say, how far can we go with this? Can we look at more complex structures? Again, if you connect to that line of work on randomized numerical linear algebra, that's basically, sketching in one form. This is sort of similarly in that vein. So there's lots of other sort of sketching techniques that I won't talk about today. Not in this talk, but do ask me about those. So what I'm really sort of trying to do is say, we have these techniques. We have reasonable facility with them that we can play around with them, put them together, come up with new algorithms. And in the context of this workshop, I think the question is, does this get us anywhere? Does this get us close enough to having a conversation with the people that have the real data that they might want to think about any of these techniques? So with that question, I will finish and turn it over to you for answers. Thank you.
Can you do anything special when the vectors are vectors of ones and negative ones? So you're looking basically for Hamming distance or something of that sort?
Yes, so my immediate answer to that question is you can't do anything more special than what we're doing already. That I think having that assumption that there is nice structure in the vectors, I don't know of any technique that takes explicit advantage of that. The advantage that I might see is if you think about the way that we build the sketches, they're based on these sort of carefully structured random transformations, which also happen to be, essentially binary -1 + 1 or sparse with zeros in. So in terms of keeping the bit representation small, if my input is discrete -1 + 1 and my transformation is discrete -1 + 1, then for sure I don't need too many bits to represent those products. So I sort of win a little bit in the sort of bit representation inside my algorithm. But I don't know if I can take a more direct advantage of that structure.
So, I guess the algorithm I would have thought of first, without having thought about this problem at all, is to imagine that you pick log n or so vectors at random, or maybe polylog n vectors at random. Compute the correlation of each of the given n sequences with those log n vectors and use that as some kind of filter. Maybe appeal to a Johnson-Linden-Strauss type dimensionality reduction and say, well, only need to check the correlation of two input sequences if the log n profile of them are kind of close.
Yeah.
These randomly chosen directions. And maybe log n's not enough, but something.
That's my initial response. I don't think log n is enough.
Maybe you can do root. You can do root n and probably beat this, right?
Yeah, maybe. That's something sort of maybe to go back to and try again. But I'm hesitant just because I'm trying to state results that work over sort of arbitrary inputs, and I guess I have to think about that a little bit more. But there might be some other things you can do to kind of rule some options out, but then you're going to still be quadratic on what remains. So you're sort of going to.
Right. But if it's root n,
what's I guess you're saying sort of pick your sort of test vectors as they were. Run a bunch of tests. So I'm going to say, okay, this input vector looked like it was. I'm going to have quite a lot of them if it's going to show any correlation, because it's going to be uncorrelated with most things. But it flags correlated with a subset of them, and then what? So these, I guess, I pick out the things that look like they've got an approximately overlapping set of correlates. tricky. And as soon as you start invoking Johnson-Lindenstrauss, I mean, I should have used the name, but this is all essentially Johnson-Lindenstrauss in disguise. These sort of sketch results, basically.
Truly related to that, should I think of your sketches in the very first or second slide? You said these need to be compact in order to be useful. So should I think of them as like a de-randomized Johnson-Lindenstrauss type?
No, think of them as a low independence Johnson-Lindenstrauss. So just to get very technical, if you think about the sparse Johnson-Lindenstrauss work, that gets you to a certain level of sparsity. So firstly, I guess I could say, I'm somewhat agnostic as to what instantiation of sketches you choose, but you probably want something that's sparse to keep it suitably fast. So the sparse Johnson-Lindenstrauss constructions get you down essentially to a 1/epsilon sparsity. There are other constructions which I tend to use and which we're using in implementations that get you down to a constant sparsity, which seems impossible, but and so the trick is it's a structured sparsity. So essentially, you do almost what I showed you in the main part of the talk, also within the sketches. You hash out to buckets. So every index in the original vector goes to some bucket. And what you argue about is that you need actually only limited independence. You need essentially 4-wise independence, because what you go through is you go through sort of a expectation and variance calculation. You need very low independence to get those to work out. But we can sort of chat more offline about how these constructions work. I mean, again, for this kind of thing, at one level, you just need whether it's Johnson-Lindenstrauss with Gaussian, whether it's sparse Johnson-Lindenstrauss, whether it's these kind of hash structured things. What this all relied on is just that you can do in a product up to additive error, and they will give you that in one form or another.
Just small thing, I'm only thinking of this may be useful. There's this sort of thing of given two GPS traces, can you say if they're following nearly the same path?
Yeah.
That way you can get these people to call. This is like a well-known
I see.
type of thing.
Yes.
And you have like lots and lots of GPS points. And
Yes. Yes.
Those correlated in time.
Yes.
Time of travel. So within 15 minutes of you and within a mile of you.
Exactly. So I think that's where this gets interesting, because I can tell you this makes more assumptions than that application would want, and we can start to play around with how could you make the two marry up. So this relies on a precise sort of one-to-one matching of indexes. It says that you're lining up xi with yi, and in your application you want to sort of line up xi plus or minus 15 minutes. And so that's I think where it could get fun. You say, either can I sort of just say, am I seeing the same trajectory at roughly the same speed but shifted in time? So you'd want to start thinking about, can I do some kind of convolution of these?
Time stamps are good enough to just start round trips.
Right, so you might just do some pre-processing to kind of say, let's kind of fuzz the time and just count approximate time since 0 and rebase everything. So that's sort of that's exactly where there might be sort of some interesting new questions to play around with. It says, okay, you can do this kind of thing, but when you have this kind of noise, this kind of perturbation, then what happens?
The problem feels as if it should be very close to nearest neighbors in high-dimensional spaces.
Yes, it should be.
Is it really precisely that problem with suitable scalings?
It's not quite the same because of we're essentially not in a metric space, but we're close enough that we need to think more about those connections, and certainly there are techniques from nearest neighbor search, essentially kind of like the sort of rejection approaches that Sampat was talking about, that could potentially be applied here. And certainly, the fundamental issue, you want to avoid doing the explicit all pairs can you question.
So the queries here come from the same. I mean, the queries are.
Yeah, so it's not quite nearest neighbor, but it is sort of nearest neighbor in the sense that people are interested in the sort of the all pairs nearest neighbor problem, I think. It's got nearest neighbor at its heart somewhere, or not quite nearest. So one of the tricky things is you're looking for large values rather than small values, and that complicates things a little bit, but I don't know that it's fundamentally different.
So I was wondering, is this easy to update over time? So suppose you have a time series which becomes correlated later on.
Yes. So that's one of the sort of the flexibilities we're looking to bake in here, because the sketches are essentially data independent. You know that you're picking the random transformation independent of the data. You can extend this, and that was sort of my concession to real time at the start. I'm saying you may be seeing new observations, and you can just slot those in very quickly to the current summaries. You still have this sort of relatively expensive search step at the end.
Is it easy to remove past observations?
Sort of, yeah. So you're into the what the computer scientists call sliding window, and it's very easy to remove past observations if you can tell me what they were, because I can just subtract off their contribution. But in general, you don't tend to remember the past observations because there's too many of them and you've forgotten them, and then you get into this sort of you get an extra at least logarithmic factor, and probably worse because you're sort of keeping sketches that cover different fractions, and you're kind of gluing them together to cover the window and then sort of slotting things around. So you can do stuff, but it adds sufficiently many logarithmic factors that any hope you had before of claiming that you were beating a space bound might start to disappear in practice. Sorry?
Discounting the past fix then?
I'm not sure exactly what you have in mind by discounting, but...
Okay. It looks like the chairman. Because Ramir has hand up. Just quick.
Quick remark, actually, sort of underlying perhaps several of the questions, right? So, whereas lengths of vectors are preserved to relative error
yes,
projections,
yes,
products or not.
That's right. Yes.
So in some sense, it's a completely different ballgame. So, Johnson, Lind, and Strauss or random projections, and perhaps also the nearest neighbor, are sort of to do with lengths, whereas this has to do with dot products. So.
It does. I mean, and normally I sort of avoid dot product for exactly that reason. That sort of the nice coincidence of structure here is that if you're looking for large correlation, then firstly you're normalized into the range -1 to +1. Your epsilon error is an additive epsilon error in there. I'm looking for things that are large, and so if I'm looking for something that's like sort of 0.6, 0.7, the sketching part only perturbs me by sort of plus or minus epsilon. So it's one of the few places where the fact that dot product is not relative error preserved but is additive error actually doesn't work completely against me, if that makes sense.
Can you use the dot product sketch to show us the...
If you don't mind, we've got 10 minutes or so. This is open discussion. Thanks a lot, Graham.
Thank you.